Меня тоже попросили на английском, поэтому я буду на английском. Okay, so my course is on Abelian varieties. My goal in this course is to present to you some basic constructions in this theory and give you a kind of understanding of what you have to be dealing with when you're working with Abelian varieties. So let's start with introduction. So let us agree on notations. We will be working over field K, which we will assume to be algebraically closed. And you may as well assume that it has characteristic 0, but everything here will work for arbitrary characteristic, and everything here can be reformulated for non-closed fields. This is especially of interest because for Abelian varieties, people mainly study their arithmetic, so they consider it over non-closed fields, for example over Q, or over number fields. And by variety, we mean a separated, irreducible algebraic variety over K. Okay, and an algebraic group is a variety G with 3 operations: multiplication, inversion, and identity. Of course, making it into a group, so they should satisfy the known axioms for a group. And the main definition: what is an Abelian variety? It's just an algebraic group which is complete as a variety. Okay, we start with an example. So, the most basic example, besides a point, besides a single point, is an elliptic curve. So, an elliptic curve is a variety C satisfying one of the 3 equivalent conditions. Satisfying one of the following equivalent conditions. So the first condition is that C is a smooth projective curve of genus 1. Curve with genus 1. Okay, the second condition: C is a curve. Okay, is a projective curve with a group structure, with an algebraic group structure. Is a projective curve with an algebraic group structure
for which there exists such a structure.
Yes, okay, for which there exists such a structure. So then algebraic group structure. And the third one is for characteristic not equal to 2 or 3, is an explicit equation. So C is given in affine part of projective plane. So in A2, we choose coordinates to have infinity at z equals 0, so x, y, 1 inside P2 by an equation of the form y squared equals x cubed plus ax plus b. And we need to have 4a cubed plus 27b squared not equal to 0. Maybe somebody can tell me what this condition means. And in other words, no multiple roots, yes. So, or equivalently, this is a smooth curve. Okay, it has a unique point at infinity, which is 0, 1, 0. This will be its identity element and infinity point. A bit about group law here. Let me remind you, how do we define a group law in such a curve? So, as I said, the identity element is the infinity. Usually when we deal with Abelian varieties, we write additively, so the identity element is 0. The inversion here, minus 0 is of course 0, and minus point at the affine part, x, y1, is x minus y. So it's a reflection with respect to the x-axis, right? And the addition is as follows. P, a point P plus point Q is equal to point minus R, where the line through PQ, the projective line in P2, meets C at R. So by Bézout's theorem, we know that every line in P2 meets a cubic at 3 points counting multiplicity. So here are 2 points, and we look for the third point. Maybe I can draw a picture, something like this. So we have P, we have Q, we have a line, and we have a third point R. Okay, and that's basically the one and only example of an Abelian variety that we will see, because even for surfaces it's quite depressing. Well, okay. Of course we have products, but this is like not simple Abelian varieties. So there is a paper that wrote this guy, Flynn. He wrote explicit equations for an Abelian surface. So X is the Jacobian. I hope we will reach this Jacobian in this course. Is the Jacobian of a smooth curve of genus 2. That is, it's an abelian surface. Abelian surface. And he embedded this thing into a projective space with explicit equations, and you guess how many coordinates there are. So it's in P15 and 72 equations.
Was it one concrete example?
Sorry?
Was that only one concrete example or was a series of examples?
I guess it's a series of examples, right? For general smooth curve of genus 2. So it took like 4.5 pages.
How many?
In the paper. 4.5 pages in the paper.
4.5?
To write the
To
72
write the
equations. So for some reason. So that's the only example we will have. And that's okay, because this whole theory of abelian varieties is basically we take a statement about elliptic curves and we try to reformulate it so that it works for every abelian variety. So you can look at this theory in this way, so if you know the theory of elliptic curves. So basic properties. Basic properties of abelian varieties, and we start with this theorem, which is general. It's not about abelian varieties. It's called Mumford's rigidity theorem. Or rigidity lemma. So I take three varieties, x, y, z. X is complete. I have a morphism. I have a point, y0 and y. I have a morphism f from x times y to z. Such that it sends this whole x fiber, x times y0, to a single point. Then it turns out that it sends all x fibers to a single point. So it factors through the projection. So there exists a unique map G from y to z, such that f is G composed with projection to the second factor. Let me draw the diagram. X times y, we can project it to 1. We have f, and so there exists this G, so that f factors through the projection. So in particular, let me write this, in particular, f of x times y is a point, right? That's Mumford's rigidity theorem. And that's the only general fact that we will prove. So let's do this where we can. Oh, maybe an example why the condition on x is necessary. If x is not complete, then it fails. For example, I can take such a morphism A1 to cross A1 to A1. So let's just send the pair xy to x times y. Okay. Then if I take one point to be 0, then I have a constant morphism, right? But if I take non-zero, then I have an isomorphism. It's just the identity map. So we need to use that X is complete. Okay, let us prove this. Well, the uniqueness part is obvious because projection is surjective, is an epimorphism. So G is unique. Follows from the fact that projection is onto. Okay. So how do we construct G? Well, it's very simple. Just take a point x0 in X and just set the map G of Y equal to F of x0 y. And if you look at this picture a little bit, it's basically the only way to define this. Well, of course, it remains to show that this F is equal to this composition. And how do we prove this? We will prove this on an open subset of X times Y, right? So varieties are separated, so if two morphisms agree on an open subset, then they are equal. Okay? So we show F equals G composition with projection on an open subset of X times Y. And now we construct this subset. In fact, we will construct an open subset in Y, and we will take X times this open subset. So how do we do this? We take W inside Z. So it's an open, affine neighborhood of the point Z0. Z0 from the state. Okay? We take this, then we take its complement. So this is closed in Z. Okay. Then take its range. Then we take its range, so F inverse of S will be closed here. Okay. And then we project this to Y. Project this to Y, and it will be closed in Y. Do you understand why?
Because X is complete.
Because X is complete, right? So by definition, the complete variety is something that when we project along it, we have a closed map. So this is closed because X is complete. And finally, we take its complement. So V is the subset we are looking for, so it's Y minus this star. And it's open. And that's the subset we're looking for, so the first thing to check that it's non-empty. We can check that two morphisms agree on an open subset, but if it's empty, then we prove nothing. So V is non-empty. And why is that so? by construction we have Z0 not in S. We took an affine neighborhood of Z0 and then took its complement. So Z0 is not in S. And then we take the preimage of S, so the image of this preimage does not have Z0, right? So we can write this as X times Y0 does not intersect this preimage. Right, so this maps to Z0, and Z0 is not in S. So this intersection is. That set is all points in X times Y, which have Y0 as the second coordinate, right? So we can write that Y0 is not in this projection. Okay, is it clear? And then finally, we delete this subset. Y0 is not in this, so Y0 is in V. Okay. So it's non-empty. And finally, we have the required equality on this subset. So F equals G on position with projection on X times V. The argument here is as follows. So where do we map X times V? Well, we've thrown out all the points in this projection of preimage, right? So we can't go into S. Yes, we took the preimage of S, so that's everything that goes into S. Then we took its projection, and then we basically lift this thing up. So we removed even more points than those who go into S. Right, so we are mapped into the complement of S, which is Data. And for any Y in V, we have something like this. So X times Y. X is complete, Y is a point, so this is complete. And it maps into W, which is affine. Okay? And we know that every map from a complete variety to an affine variety is constant. So we have f of x0y equals to g of y equals to f of xy. For all x. And that's what we want. It does not depend on x. Okay. So that's Mumford's rigidity theorem. And we will now actively use this to deduce some basic properties of Abelian varieties. The first one being is this, I guess, not so well known in this form property. So if I take an Abelian variety X, X is an Abelian variety, and G is just an algebraic group. Morphism F from X to G such that it maps identity element to identity element. So identity elements. So a map from an Abelian variety to any algebraic group which maps identity to identity is a homomorphism. F is a homomorphism, is a group homomorphism. So it respects the group law. Okay, proof. Well, we use Mumford's rigidity theorem. We consider the map P from x times x to G, which maps a pair xy to, well, the difference between this map being a homomorphism. So fx, fy, fxy inverse. Right, so we see that P of x times identity, if we substitute identity into y, this will be identity in G. It's easy to see, I guess. So we use 1, 1. To deduce that P of x, y, it does not depend on x, so it's equal to P of EY, and it's again E prime. And this means that for all x and y, and this means exactly that this is a homomorphism. Okay. And well, a couple of corollaries. So the maps like this, they are homomorphisms, and if I have an arbitrary morphism, I can turn it into a homomorphism by composing with a translation, right? So, X abelian variety, G again algebraic group. Again we have a morphism. Just any morphism and denote f of E equals G. Then we can compose with translation map to obtain a homomorphism. This is a homomorphism, and here, I'll write it here. So this TG inverse, this will be my notation for translation. So notation for an algebraic group G and an element G in G, we have this translation map which translates by left multiplication by G. And another corollary. So the first thing to note here, that Abelian varieties are isomorphic as varieties if and only if they are isomorphic as algebraic groups, right?
Each such variety admits only one structure.
Not only one. Okay? That's the second point of this corollary. So X is a Abelian variety, then there exists a unique group structure on X such that a given point is the identity. Because I can always translate this operation to make any point is the identity. Okay, so those are, I don't write a proof because they just straightforward follow from this proposition, right? And another corollary, so we call them Abelian. Well, they are commutative as groups. Abelian varieties are commutative. As groups. Abelian varieties are Abelian groups. Okay? And it's happy news because otherwise this theory would be horrible. So how do we prove this? Apply 1.2, this proposition, to the inversion map. Inversion, I will usually denote this by iota x to x. So, of course, inversion maps identity to identity, so it's a homomorphism. And the inversion map is a homomorphism if and only if the group is Abelian. I hope it's clear.
So this is a direct check, right?
Yes, I think you can check this in your head in like 2 seconds.
Which place to rest?
Is it clear?
Yes.
Okay. Okay, and some another notation remark. As I said previously, usually we write the group law on Abelian varieties additive. So the group law on Abelian varieties is denoted by. But still we will denote the identity element by E. And this will cause a lot of confusion when we come to divisors later, I hope. Okay, and a bit more, just I guess I find it interesting, a couple of results which we will not prove. If I have a smooth variety y is smooth, x is a Abelian variety, and I have a rational map from y to x, then it's a morphism. So every rational map from a smooth variety to an Abelian variety is a morphism. And the idea is just to combine two general facts. The first one being that if I take a normal V and complete W and a rational map from V to W, by phi maybe. Then it's a well-known result that phi, the indeterminacy locus of phi, so the set of points of phi is not defined. The indeterminacy locus of phi has codimension at least 2. That's the first fact. And the second general fact, that if I have a smooth variety and I map it into an algebraic group, so G algebraic group, and I have a rational map, then either it's a morphism or the indeterminacy locus is a divisor, right? So the indeterminacy locus has pure codimension 1. So it's a divisor, it's a support of a divisor. And I guess you can see how we combine these two facts and get this. So it's both has codimension at least 2 and pure codimension 1, so it should be a morphism. And the funny corollary, so everything is even worse because Abelian varieties are isomorphic if and only if they are birationally equivalent. They are
even better.
Even worse. Even worse because it's even less hope to obtain another example, right? So that's some basic properties that I want to tell you about. Now we move on to something a bit more tedious and scary. So now I want to talk about invertible sheaves. On Abelian varieties. I will try to introduce this stuff as gently as possible because I know that we don't really do this kind of stuff here, okay? So let us recall. We will need the pullback stuff. If I have a morphism of varieties, morphism of just any varieties, and I have a sheaf on Y. L is a sheaf of Y modules. And once again, we will only consider invertible sheaves, which are a lot better than arbitrary sheaves. Then we have a pullback. Pullback F star L. This is a sheaf of OX modules. Sheaf of OX modules. Well, there's a concrete definition I don't want to talk about. I want to tell you about this in particular case. So, okay, in general, F star is a functor. And it commutes with both tensor products and, in our case, with the inverse, the dual sheaf. Okay.
What do you mean by our case?
Well, pullback functor commutes with dualization for locally free sheaves of finite rank. But we consider only invertible sheaves, so those are locally free of rank 1. But this is for general sheaves, but for invertible sheaves, we recall that invertible sheaves modulo isomorphism are in bijection with line bundles on X. Line bundles E to X, again modulo isomorphism, and in one-to-one correspondence also with Cartier divisors. Here, divisors on X modulo linear equivalence. And in terms of, well, this thing can be defined in terms of invertible sheaves, but we can also define it in terms of Cartier divisors, which is a lot simpler. We just take, well, recall that Cartier divisor is the set of data. We have an open cover, we have functions on each open subset, and we can just pull back every function, right? This is a lot simpler to understand. And for line bundles, how does it work? If I have a morphism, I have a bundle here, say pi. Then I can just take this categorical pullback, or what's it called, fiber product, right? So I can just take fiber product y times E over X. And this will be our pullback of E. I hope something became clearer after this.
Well, you can also say that you, like with Cartier divisors, you can cover your variety where one and one of two arises.
Yes.
And then just pull back for cycles.
That's the sense. And we will do a lot of pullbacks, so I hope you're not scared of them. And I will need another general theorem here. And maybe also about restriction. So if I have X variety, L sheaf on X, and a closed subset, say S. Closed. I can restriction. I can restrict my sheaf to this closed subset. How? I just take the inclusion map S into X and just pull back this L. Right? So it's even easier when you look at the line bundles, you just basically restrict. Okay. Guess I will need another sheet. Is it okay? Yeah. Maybe they are limited already. So I won't prove this, but I will need the statement. This is so-called theorem of the cube. Theorem of the cube. And it starts familiar. I have 3 varieties, but this time 2 of them are complete. X, Y complete. And we take points, X, Y, Z points on X capital, Y capital, Z capital respectively. And finally, we take an invertible sheaf on the product. Invertible sheaf on X times Y times Z. And And we assume that this invertible sheaf has this property. Its restriction to each subset of the form, restriction of L to each. So when I fix a point on one variety and restrict my sheaf on this closed subset, I get a trivial invertible sheaf. A trivial sheaf. So each restriction to each x times y times z, similarly x times y times z, and x times y times z is trivial. Then it turns out that L is trivial. So if my sheaf restricts on each of these subsets trivially, then this sheaf is trivial. And it looks kind of strange, right? So we have only 3 closed subsets, which is a very small portion of our variety x times y times z, but nonetheless, this basically defines the whole sheaf L. Okay.
And of course, it's important here that x and y are complete, right?
Of course, it's important, but I don't have a counterexample. And of course, I can write also if and only if, right? So if I had a trivial on the whole x times y times z, then it would trivialize on each restriction. So you can look at this. This direction is straightforward, and this is like the theory of thinking. Okay. So here, and we will use it a lot in the following theorems that we prove. So the first one, so in this section I will need some like strangely looking results about some sheaves, about some pullbacks that will you will not understand why do I need this, but it will come later into the great picture quite nicely. So, the first one is as follows. I take an Abelian variety x, I take an invertible sheaf on x, and then for any variety y, and for any morphisms three parallel morphisms, so y to x, 3 parallel arms, f, g, and h. We have something like this. So I can consider its sum, right? So I can pointwise sum all my morphisms because I have an operation here, okay? Then I can take a pullback of this and apply it to L. And then I will obtain this horrible thing. So it's somewhat, I don't know, half linearly goes like this. So it's f plus g, then tensor with f plus h, tensor with g plus h, and now just f, L inverse g, L inverse and h, L inverse. So how can you look at this? You can think about the divisors. You can think about the divisors, and so pullback of a divisor And so it's kind of written here that a divisor plus, which is shifted along the sum of three things, is just divisor shifted along the sum of two, sum of two, and then minus, minus, minus. So those are basically, when I take dual, it's minus. So it's 2 times f, 2 times g, 2 times h, minus f, minus g, minus h. Okay. I'm not sure if I have to shoot this.
What is the use of this funny corollary?
Well, we will use this for slightly less funny corollaries later. I don't think it's too enlightening to prove this, so I think we can just skip this, okay? Okay. And we can skip this to immediately get so we had theorem of the cube, we have its corollary, and now we have theorem of the square. Of the square. And for this we will have some geometric interpretation, so it's not so strange as the previous one. So again, I have an Abelian variety, I have an invertible shift on x. Then recall we have the translation maps, and I can pull back by these maps. So to pull back by a translation map which adds x plus y is the same as pull back by just x, tensor with pull back by just y, tensor with L equals. And now we can remark for divisors because it makes a lot of sense. So remark. If we look at the divisors, what do we get? Well, what is a pullback?
So we use L in the second.
Yes, thank you. If we look at the divisors, what do we get? Well, we take L invertible shift and its corresponding divisor D. Right? Divisor, so Cartier divisor. Or just Weyl divisor because our varieties are small. Just Weyl divisor. And what is a pullback of this invertible shift? What's the corresponding divisor? Well, it's just the shift of this D by the translation map minus X. Okay, and so then what's written here? What's written here is something like this. So 2.3 in terms of divisors. If I shift by minus x minus y, this D, this divisor will be equivalent to shift by minus x plus shift by minus y minus D. And it becomes even more clearer if I rewrite this as follows. So shift is basically, we do what? We subtract from each point of D x and y, right? So this is equivalent to D minus x plus D minus y minus D. So there are different operations here, so those are minuses as in variety, and those are plus and minus in class group, okay?
Great question.
Yeah, so you sum them just.
In Veil divisors, okay. But it's tempting to just remove the brackets, right, and to mix up those operations and get just the simple equality, right? And we will do this a bit later. So basically what it does, this theorem of the square, it provides us with a homomorphism from our x to the class group. Okay. We will use this to get this homomorphism from x to its class group. So it's now not so strange, and we can maybe prove this even using this unproved corollary. Okay, proof. Well, just use 2.2. Use 2.2 for very specific morphisms. So we take y equals x, f is constant to x, g is also constant, so it's constant, and h is just identity. And let's see what we will get for these morphisms. Yeah, maybe I should have written this one here because it's more important. Maybe let me just rewrite this. F plus G plus H. F plus G. F plus H. G plus H. Okay, so what will happen when we apply this stuff here? So here we have what? So f plus g plus h is what? When I sum all these maps, I get what is this map? Do you understand? If I add the identity map with this constant and this constant, what do I get? Shift by x plus 1. Right, so then f plus g, I sum two constant map, I get the constant map to x plus y, right? F plus h is again shift by x, and g plus h is shift by y. And so we have pullback by this. Isomorphic to pullback by constant map, tensor with pullback by this, tensor with pullback by this, tensor with Constant map, and identity. And do you understand what is the pullback of a sheaf under a constant map? So you can take one. What is a constant map? It factors through a map to a point, right? And so the pullback is two pullbacks. So when I pull back here, I get trivial here and then trivial here. So those are all trivial. So those are trivial. Okay, yeah. Thank you. So those are all trivial. So those are all x. Okay. This one is just nothing happens under the identity map, so we get exactly what we need, right? So we are left with this, and with this. I don't have this statement anymore, but that's what we want, right? Okay, so my time is up. Do you have any questions so far?
Questions?
So what are we going to do with this?
Yeah, then I will start with another small lemma like this, and then we will use this all stuff to firstly prove that, well, as I said, we have a homomorphism from the Picard group from X to Picard group. We will use it later to construct the dual Abelian variety. And also we will use this stuff to prove that every Abelian variety is projective.
More questions? If not, let's have a